Hi there, in this video I'll be talking about study design basics and some measures of effect that go along with them. So quickly, the learning objectives are to talk about why observational studies are important in public health, to distinguish between observational and experimental studies, and specifically we'll talk about cross-sectional, cohort, and case control studies as examples of observational studies. We'll also talk about how to calculate and interpret both relative risk and an odds ratio. So first, a little recap and setting the stage for why we're talking about this. So as a reminder, we've talked about descriptive epidemiology up to this point. So remember, that's kind of the person, place, and time variables. And that's a very important aspect of epidemiology and public health work, understanding who's experiencing health exposures, diseases, events, where they're distributed, where they're happening geographically, and what trends look like over time. So both across years, across seasons, across different time scales. And so these descriptive measures can help us look at things like incidence and prevalence and make some decisions about how to prioritize health topics and health issues, but they don't tell us about what's causing these health issues, health events, health outcomes that we're concerned about. And so that's where we need to move into this more analytic epidemiology. And so I think of two broad classes of study design types, experimental and observational. And for many reasons, but probably the predominant of which is ethical reasons, a lot of times in public health, we end up doing observational studies. So this is where we're just watching what happens naturally. We as researchers are not instituting any kind of change to people's lives or experiences or environments. So there is no intervention an observational study. And so that's really the distinction between the two. We're not randomizing anybody to be exposed or not exposed. We're not developing or designing some specific program or service or situation that we're trying to study. We're just seeing what people's natural behaviors and choices look like and how those relate to outcomes. So to think about these different kinds of observational studies, one thing to do to start with is to think about the population in terms of people who do and don't have the disease that you're interested in. So the green shapes represent people who don't have the disease and red shapes are people who do. And the first example, maybe the most basic type of study design, is what's called a cross-sectional study. And so in this type of study, we're just taking a sample within that population. So it might be a random sample, ideally it would be. Sometimes it's a convenient sample, but we're taking a group of people out of the population and just looking at them. So we're going to get a mix of people who do and don't have disease. We're going to get people with different types of exposure. And in a cross-sectional study, it is defined by the fact that it's a single time point. And so we're asking about both the exposure and the outcome at the same time. So you can think of it kind of like a cross-section in a biological sense. So that's a picture at the top is like a slide showing a cross-section of some tissue from the body. And so it's the same idea. We're taking a cross-section, a look at just a slice of the population to understand what might be going on. And so because we're looking at both exposure and outcome at the same time, cross-sectional studies only give us information about prevalence, so what's currently happening. We're not following people over time to see who develops new cases of disease, that incidence measure. So these are helpful for looking at what are patterns in the population. And we can look at associations using cross-sectional studies, but for reasons we'll talk about in the next session or two, it may not be causal. So because we're asking at the same time, we don't know which order things happened in. So maybe, if we're looking at whether, let's say, stress impacts heart disease and we're asking about both at the same time, we don't know if the stress came before the heart disease or if heart disease happened first and then the stress. And so that's one of the major issues, what we call temporal sequence problem. There's a time order issue. We're not clear about which one happened first. And so that makes it less likely, or we'd be more concerned saying that one causes the other because we're not sure what order they happen in necessarily. So that's cross-sectional study. The next type of study that we're going to talk about, again, this is an observational one, is a cohort study. And so in order to do a cohort study, we're still going to take some sort of hopefully random sample from within our source population. But this time, we are going to exclude people who already have disease. So we're starting with all people from the population who don't have the outcome we're interested in. And we sample a group of people who have been exposed to whatever we're interested in, another group who has not been exposed. We follow them both up over time, and we're looking at incidence here. So this is one benefit over a cross-sectional study. Cohort studies are over time, and so we can look at incidence. This is another way to think about the steps of it. And going back to just a quick reminder about risk, because we're going to talk about relative risk as the measure that we calculate in a cohort study. Risk, again, is a probability, so basically just means the chance, and we're usually talking about the chance somebody develops a disease, has a health outcome, experiences some health event that we're interested in. And at risk just means there is a non-zero chance, non-zero probability of developing that outcome. So to calculate relative risk, we're really just comparing incidence in our two groups. So in this case, we're going to compare the incidence in the exposed portion of our cohort to the incidence in the unexposed group. And the way that we calculate that in kind of the crude way is to set up what we call a 2x2 table, which is shown here on the slide, where we have the exposure in the rows and the outcome across the top. We label those columns A, B, C, and D, or the cells A, B, C, and D. And so the incidence in the exposed group is A divided by A plus B. So the people who are exposed and have the disease out of all of the people who are exposed. And then the incidence in the unexposed group is just C over C plus D, which again is people who are not exposed to develop disease out of all of the people who are not exposed. So if we get a 1 for this measure, if the incidence is exactly the same, we would get a relative risk of 1. And so that means the risk of the outcome, the chance of developing the disease, is exactly the same in both the exposed and unexposed groups. So there's no association between the exposure and outcome. If the relative risk is bigger than 1, then going back here, if the numerator is bigger, we'd have a relative risk greater than 1. So that means the incidence in the exposed group is higher. So that means people who are exposed are more likely to have the outcomes. So that's what we often call a risk factor for the disease. And then if the relative risk is less than 1, that means that having the exposure actually decreases the risk of disease. So we call that protective. So cohorts often require a long period of follow-up because you're starting with people who don't have a disease and waiting for them to develop it over time. There is a way to do a retrospective cohort. So that means you start now and look in the past. So this usually requires having some sort of records, medical records or something else to accurately classify people as exposed or not and making sure they didn't have the disease at the start of the time period, but that can help. So that means, especially when there's a short duration between exposure and outcome, cohort study is a good option. It's also good when the exposure is rare. Since we're sampling based on exposure, then we can make sure we have enough people in our exposed group and in our unexposed group if we do a cohort study. So advantages, you can have really large cohort studies, and so that's nice. Again, the duration can vary. You can make it shorter. Sometimes they're longer though. Again, it's good for rare exposures because you're sampling based on exposure status. We know that exposure is coming before outcome because we're excluding people who have prevalent disease at the beginning. And again, we can measure incidence. So because they can take a long time and can be large, that can also make them costly. It's hard, it might be hard to recruit people and to keep them in studies for long periods of time. And so you might end up with dropout, high levels of dropout. And it's not good for rare outcomes. So if we're following lots of people, even if it's a huge number of people and maybe only 1 or 2% of them will develop the outcome that we're interested in over the study period, it's not gonna be enough events, enough outcomes. So we do need to think about doing things like power analyses heading into designing any study. So the last type of observational study we're going to talk about is a case control study. And this is kind of like the reverse of a cohort study. So in this situation, we're still drawing a sample from the source population. And instead of sampling based on exposure, like we did in a cohort study, we're now sampling based on outcome. So we pick cases and controls in a case control study, hence the name. So cases are people who have the disease, controls are people who don't. And then you ask them about their past exposures. So usually we're doing maybe 2 controls for every case or 3 controls for every case. It depends on how you want to design your study. And sometimes there's matching. So that's one kind of advantage of case control studies. you can control for some confounding in the design by, for example, picking the same number of men and women or picking the same number of people in different age groups in your case and control groups. So the setup for analyzing a case control study is the same. We can still use a 2x2 table, but because we are picking how many people do and don't have the disease by design, we can't calculate incidence. And so we have to calculate the odds ratio instead. And odds ratio is sort of similar to a relative risk, except that instead of directly comparing the probability, we're comparing the odds, and odds are the probability over 1 minus the probability. And so when we calculate on the 2x2 table, it ends up reducing to this cross product. So we're doing A times D divided by B times C to calculate a relative risk from a 2x2 table. I won't go through all of the rationale for why we get there, but again, because the odds is probability over 1 minus probability, when you divide those out, that's what it reduces to. So we interpret an odds ratio essentially the same way as a relative risk. 1 means identical odds in both groups. If the odds ratio is greater than 1, it means the exposed group has higher odds of disease. Odds ratio of less than 1 means the exposed group has a lower odds of disease. But just note that we're not measuring risk here, we're measuring odds. So when you interpret them, you really should use the word odds instead of risk. It doesn't happen all the time, but something to be aware of. And it's particularly important because an odds ratio ends up being similar to the relative risk when the outcome is rare. So when the disease risk in the population is less than about 5%. But as the outcome becomes more common, the odds ratio is no longer similar to the relative risk. So interpreting it as if it's the same is not really accurate for the studies in those situations. So case control studies are a good option when you have a rare outcome, because again, we are sampling based on outcomes, so we can make sure we have enough cases and enough controls. They typically take less time than a cohort study because you're not following people over time. You're probably using some sort of records or existing data for much of your information. And again, you can match cases and controls on important factors, so that can limit confounding. And since we're sampling based on outcome, you can actually look at multiple exposures in a case control study. However, finding those cases can be challenging. Matching people can also be difficult. And just like in retrospective cohort studies, you need to make sure you have good historic information to do this. And they're not good for rare exposures. So I'm not going to go through this slide in detail, but we talked about pros and cons, so those can help you decide whether you want to use a cohort or a case control study in a particular situation. So I want to wrap up with just talking briefly about experimental studies because they are an important class of study. And we use them a lot in public health. So this is one example, something like a bed net intervention to try to reduce malaria by keeping out mosquitoes. That's a situation where we could do a randomized trial or an experimental study. And so the basic design for an experimental study is to take a sample from your population, again, ideally random. You're going to have some people who choose not to participate, and among those who do participate, you would randomly assign them to either get the intervention or get some control. It might be a placebo, it might literally be nothing, it might be something else. Even once people are assigned to their groups, you're going to lose some of them over time, but then ultimately we're going to measure the outcome in the intervention and control groups and compare them to one another. So randomized control trials are probably the most common type of experimental study done in public health. Medication drug trials are a very common example, hence the picture here. And even though they're often considered the gold standard of excellence, it's still important to kind of scrutinize them carefully because there's still lots of ways in which, although the design does reduce the likelihood of having bias in your results, if you draw a poor sample, take poor measurements, lose a lot of people differentially over time, then they're still not going to give you very strong evidence. So those are the kinds of things you still want to think about, look at when designing or evaluating randomized trials. You want to make sure that people are randomized. The purpose of this is to evenly distribute any potential confounders across exposures. So if something happens that makes a particular group of people more likely to get assigned to the intervention arm, that's problematic. You want to look at what type of control group there is. So typically we use some sort of placebo, which is defined as a biologically inert substance. And the reason is because getting care, treatment, attention, even if it's not specifically designed to improve the outcome you're looking at, often has beneficial effects for people. So you do want to account for that. There should be some sort of control in any kind of experimental study. Whenever possible, it's good to blind people. So this might be not telling subjects whether they're getting the exposure or not, whether or not they're in the intervention or control group. So that's relatively easy to do in something like a drug trial. Clearly impossible to do in something like a mosquito net trial. But you can also blind people who are doing the assessment, so going out and doing the follow-up measures. You could blind people who are doing the analysis. So there are multiple ways to blind people so that it doesn't bias any of the measurements. You also want to think about inclusion and exclusion criteria and who you're losing over time. So this really just relates to, are your results generalizable back to the general public or just to a subset of people? And that, I think, is one of the bigger issues that people often skip over in thinking about randomized trials. Who does this really apply to? And finally, as I said, in public health, there are so many exposures that we're interested in understanding better, but we know that they have harmful effects. So it's just not ethically possible to randomize a whole host of things to people at this point. So often we, again, end up doing observational studies. One note, well, I'm going to skip the community trial part. So again, experimental studies give us strong evidence of cause and effect when designed well, when the measurements are good. And largely this is because we can limit some of the confounding by the randomization process. They also allow us to potentially evaluate a dose response, which again, we'll come back to when we talk more about causal inference. But you can give people different levels and see how those translate to outcomes, differences in outcomes. The drawbacks are that they can be really hard to recruit people for, and they are generally pretty time consuming and costly. As I said before, we may not ethically be able to do them in every case. And again, there may be people who are either not able to do the full intervention or who drop out early, and that can impact results. And so I do want to note just generally about sampling groups, both in randomized studies and in observational studies. It's possible to look at the group rather than individuals as the unit of analysis. So by this, I mean, if you wanted to compare schools or compare neighborhoods or census tracts or states, those are all groups rather than individuals that might be your unit of study. And so they can be really informative, especially for things like policy evaluations. But it is important to consider whether what you find at the group actually holds at the individual levels. So this is what we call the ecological fallacy. Sometimes we see associations between groups, but when you get down to the individual level, it's not important, or it doesn't hold, it's not the same association. So it is important to do both group and individual level studies. And again, just think carefully about who was being sampled and then what are the actual implications based on that. So as I said before, the next step in this will be looking at, okay, these studies are primarily all designed to identify causal factors. Is an exposure causing an outcome, and therefore can we intervene on it? But it goes beyond just knowing what the study design is. There's different aspects we want to look at, and so that's what we'll move into talking about next.